Good morning, everyone. Now we are familiar with synthesis of graphene properties, characterization, surface functionalization, as well as how we can tune the optical as well as electronic properties, or we can say how we can tune the band gap. So again, if you remember, 2D materials are not only graphene, there are a lot variety of materials are here. And we also know based on their composition, we can give different name. So either they are single element base or they are having basically a compound. So today I would discuss at least the two known materials under two-dimensional material other than graphene. And in overall discussion, what we are going to talk about, so though we can say there are a lot of materials, but here I'm just going to discuss few which are slightly more popular under the two-dimensional material consideration. So the first one is silicene. The name you already know. If we are adding "ene" means it's a single element based material, and silicene means it's basically based on the silicon. Similarly, the second one is germanene. The next one is phosphorine, stenine, transition metal chalcogenides, and amexine. So, other than graphenes, we will discuss only these six materials. And if you remember, the silicon and the germanium and the carbon are fall into the same group in the periodic table. So their structure is also look like almost similar. We will do talk about other things like how the differences are there. So let us start with the silicon. Why? Because when the graphene became very popular, and even in 2010, when the discovery of graphene received the Nobel Prize, so many researchers have started working on two-dimensional material, and silicon was the first consideration. Reason being, we already having the existing technology which is based on the silicon semiconducting behavior, and therefore people are trying to understand if we can create a monolayer of silicon, then maybe we can achieve the properties similar to that we are basically having in case of graphene. So having the same ideology, there were a group who were working to basically synthesize the silicon monolayer, and the name was given as silicene. So here you can see few technical news at that time. So I'm sharing here, this news was basically in 2011. They are saying that silicon might be the new graphene now that it has been physically constructed. So theoretically already there was several investigation, but it was very difficult to fabricate or synthesize silicene. The reason being, as in compared to the graphene, we are already having a layered structure that is known as a graphite. So using graphite, it is easily we can separate the layer of graphene. But in case of silicon, such kind of layered material is not available. So it's very difficult to fabricate the monolayer or the bilayer of silicon. So here we have to go as basically bottom to up approach. We have to synthesize a monolayer. So therefore it was not so easy, and people was trying, and in 2010 they came up with the idea that it can be synthesized. So then it became popular in the news. I would just share a few more. The next one is April 2012. New Scientist says, moreover, graphene, silicene is the new star material. Other news, electronics, they said silicene, the new graphene, question mark. They are saying basically, can we expect the similar property as we are getting in graphene, or can silicene replace the graphene? So this news was published in 2014. Another one, the first silicene transistor has been fabricated. What is mean for the computer? So this was again get the highlight, like if we are preparing the silicon based transistor, similarly we can also prepare the silicene based transistor, and can it will be useful, or can it give a better performance in terms of data storage, data transfer, or the application which is related to the computer. So let's say what we can say, the graphene is there. So basically silicene is also a two-dimensional allotrope of silicon, similar to the graphene two-dimensional material of carbon. It also has hexagonal honeycomb structure similar to the graphene. Moreover, this material also has sp2 hybridization, but this is not entirely, it's dominate sp2, but it also consists some of sp3 hybrid bonds. Similarly, this material also has a linear band dispersion behavior as we have observed in case of graphene. Moreover, since this is having a linear band dispersion, its electron behave a mass-like Dirac fermions, and also it shows a very high carrier mobility, similarly as we have seen in case of graphene. I would suggest you just go through this reference for more detail about this material. The structure of this material we can understand by looking this figure A. So figure A shows the planar structure where the 6 atoms 1, 2, 3, 4, 5, 6 are having a hexagonal pattern, and we can say this is a flat similar to the graphene, but in case of silicene the structure is not really flat as we have observed in case of graphene. Here at least the alternate atoms are having some buckling or up and down structures. You can see here at my pointer, this atom is slightly up, this second atom is down, then this atom is up, then this atom is down, up and down. So basically it is having a little bit up and down structures, ripple or buckling, we call it buckled structure. And if we see about the angle between the flat surface to this buckle angle, then we can decide whether it is having sp2 hybridization or sp3 hybridization. As you can see in figure B, if it is flat, then this is sp2. There could be a possibility where this angle theta, basically with angle with respect to flat, it come in between. So it may be the sp2 and sp3 intermix in or in between, and if it is having the theta larger than that, then it is can be considered as sp3 hybrid system. So here basically we are having not exactly planar symmetry, it is a kind of buckling structure. And if we talk about silicon bond length in buccal state, then it is around 2.247 angstrom, which is slightly longer than the flat. In case of flat, it is around 2.226 angstrom, basically the distance between silicon atom to silicon atom. So this is the typical structure of silicene. And here, since we are having a buccal structure, then the electron is even not so localized or slightly less localized as compared to the graphene. Similarly, since we are having a buccal structure, there is a chance to have a partial sp3 hybridization, which is the second mark difference with respect to the graphene. So if you are comparing these two materials, graphene and silicene, then we are having a basic difference. This structure is not having very flat. Here the silicon atoms are having sequential up and down structure, and we are calling it a buccal state. And due to this buckling, all electrons are not ideally localized. They are slightly delocalized. Moreover, here we are also having the partial sp3 hybridization. So having mixed sp2 and sp3 hybridization due to the buckling, basically that we can understand the angle gamma. That is basically the angle of silicon to silicon atom as compared to the normal plane. And if we can manipulate this buckling, or if this buckling is there, that is basically giving a difference in the band. Here, since buckling is there, in case of silicene, we may have some band gap opening. Similarly, the electronic structure will be slightly different, and even by doing some kind of selective chemical activities or modification, we can again manipulate the band gap and electronics properties. So electronic band structure, buccal silicene appeared as a graphene-like direct crystal where pi and pi star band cross linearly at the direct point. So it's a similar as we have observed in case of graphene, namely high symmetric K and K point in a hexagonal brilliant zone. So here the brilliant zone is also look like similar. We are going to have pi and pi star bands, and we are having a symmetric point, direct point. Similarly, as we denote into K and K0. I would suggest you should go with this reference for further detail. So now how we can synthesize the silicene. So because we don't have any layered structure as we are having in case of graphene, so how we can synthesize? So we have to just synthesize in the laboratory by adopting the bottom-up approach. And this is the first study. Epitaxial growth of a silicene seed was published in Applied Physics Letter in 2010. And the report says they have grown silicene seed on silver 111 substrate under very high vacuum conditions. In this growth, first they have treated the silver substrate, they clean it several times, then by sputtering, the cleaning was done by basically sputtering the atoms, and then it was annealed at 400 degrees Celsius to achieve a specific orientation as well as a very uniform surface or smooth surface. Then silicon was evaporated by direct current heating using a piece of silicon wafer, and this silicon was then deposited on silver 111 surface at temperature 250 degrees Celsius. So this was the basic point. Further detail, again I would refer to go through this Applied Physics Letter. Here is the STM image, atomically resolved STM image, and as you can see in figure A, a perfect atomic resolutions is there. You can see each atoms, and here again we can see the atoms are basically having a kind of hexagonal pattern. You can see any of these. So it is again look like a similar structure as we observe in case of graphene. And figure B shows here it also covers the up and down or the topography of a substrate, similarly as in case of graphene. So almost the surface look like similar to the graphene structure. This is again the atomically resolved STM image. So figure A is the surface of silver. So basically, if we are willing to grow silicon monolayer or bilayer, first of all we have to go to develop the silver substrate, and you can see all atoms are perfectly visible here, and they are also having very perfect atomic alignment. And figure B shows the once this silicon, so you can see atom here, this bright atoms, basically these are the silicon atoms are here. So these are the silicon deposited over these silver atoms. So even the size of silver atom is large as compared to the size of silicon atoms, and that we can understand basically by looking this kind of model proposed by this group, where you can see this bottom color, these are the silver atoms which are large in the size, top of which when we are growing the silicon, so these silicon atoms are in the black color. So this kind of depositions are happen when we are growing the epitaxial growth of silicene. And here the observation also shows there are some point where the silver atoms are occupied with the or covered with the 6 atoms of silicene. So that time we are calling it a superstructure. So silver atom showing the silicon superstructure, and a peak to peak analysis of distance between 0.1 nanometer and 0.2 nanometer, while a value to value analysis indicates silicon distance of about 0.18 to 0.1 nanometer. This is the other research article published again in Applied Physics Later, entitled as Single Domain Epitaxial Silicon on Diboride Thin Film. Single domain means here they have first grown very small domain of the silicon, and there they are calling like if we are continuing supplying the source of silicon, we may also convert this single domain into the large sheet. So epitaxial silicon form spontaneously on ZrB20001 thin film, and which were grown on the silicon. So basically silicon wafer, then ZrB2 film, and then top of that they have grown the silicon monolayer. So here they are saying that by absorbing additional silicon atom on the surface, we find that the domain boundary vanishes. So means earlier it was having the domain boundaries, but if we keep applying the silicon atoms, then that boundary will be not there, and a single domain silicene sheet can be prepared without altering its buccal honeycomb structure. And here this figure says it's clearly, like if you see the figure A and C is basically again the how this is going to mix up. So see, these are having a one domain, then this is another domain, this is the next domain. So they are saying the similar, this domain can be converted into a sheet if we are keep supplying the silicon atoms, and they are just giving the modeling how it can be achieved. So now the next recent article it published in Advanced Material in 2019. So earlier all the studies was based on the very high vacuum based synthesis, and which is some sense not very favorable for some sort of applications, though it's very good. The properties is very relevant and can be used for electronics application, but some other applications may require slightly large amount of material as well as transfer of material is required. So the another approach, wet chemical exfoliation, was reported, and here basically the idea was similarly as we were trying in case of graphene, but it's not exactly taking the silicon because we are not have a silicon layered structure. So here they use a gentle phase of CaSi2 crystal. So this crystal is having some kind of layered structure, and then it was put in the CS3CN solution and iodine also. So how we are going to get the layer of silicon? So they are saying that layer binary silicide, that is CaSi2, when we are using this, we have to remove Ca somehow, right? So if we introduce some chemical that can bind with Ca and it can remove Ca from the structure, then we are going to have the silicon layer. So same thing they have did. They said that the silicon layer was oxidized by iodine through an outer to inner diffuse process, and we are getting the byproduct of CaI2. So, and then CaI2 was dissolved in the solvent. So first Ca is interacted with I2, which forms CaI2. Now what we are having the silicon atoms, and then the CaI2 is also dissolved in this solution the same time. So now what we are having basically a single or a layer of silicon. So monolayer of silicene nanosheet precipitate was thermo-expanded. So now it was there, but how we can do the expansion or exfoliation, since we are having the layer of silicon. So it was thermally expanded at 380 degrees Celsius and subsequently emerged into the liquid nitrogen. There is the quenching also until the complete evaporation of liquid nitrogen in the container. So in this study, they have achieved the freestanding silicene nanosheet, few are single layer. We can understand this paper by looking this diagram. So figure A shows the experimental procedure where we are having C2S3N mixed with this precursor. Mild oxidation and extraction is happened. Here it's formed a CaL2, then thermal expansion was done to achieve the sheet, and then again gas exfoliation to separate out the sheet. I think the figure B shows the sequential result here. We are having CaSiO2 material, SCM look like this, figure C. D shows the atomic alignment of silicon and Ca. So that's why they have given the two different color. The color red is Ca, the color green is silicon. So you can see the sequential green, red is there. Even this Fourier transform also shows the similar light. They are having a layer by layer, one atom, then let's say one atom of silicon, then another atom of Ca, then silicon, then Ca, then silicon. So this structure is there. Then when they have basically separated Ca, so this is multi-layer of silicene. You can see a layered structure, so layer by layer. So Ca is removed, now silicon is there, and even it's very clear if you are looking this image H and I, this SCM image shows the layered structure, which was earlier not there. And this TM image also shows the single layer of silicon. Then when it was exfoliated using liquid nitrogen, then gas exfoliation, then you can get the sheet and which is basically here the disperse that shows the CM image, and this is the TM image, shows a single sheet of silicene. Again the silicon and the Ca, you can see the atomic percentage, so it shows there is only silicon, no Ca is available, means it confirms the formation of single layer. And again this selected area electron diffraction pattern confirm the crystalline structure. So this was all about silicene. So just I have given a very brief, and if you are interested, you go through these literatures. Now the next class of material is germanene. So this is again the same, because it's again under the same category or the same group, silicene and germanene. So, but it also received a lot of popularity So after silicene, the germanium was came into the picture, and the graphene get a cousin in the shape of germanium. This was the news. Another news says first graphene, then silicene, and now germanium. So it was in September 2014, 11 September. This news was 10 September, and then the graphene family tree, germanium, its appearance. So basically, they are saying the carbon atom, the silicon, then germanium. So it's tree. The structure is again here similar as we have seen in case of silicene. The germanium honeycomb lattice is buckled and composed of two vertical displaced sublattice. So again, one atom is up and down, as you can see in the figure B. So similar structure as we have seen in case of silicene. Here again, the structure is having a monolayer, so therefore the confinement of electrons are there, and we are observing the direct equations. And this case, what one more important point to note, that is the spin orbit coupling gap in case of germanium is very high. It's 24 million electron volt. It's much larger as compared to the graphene, and this high voltage make it very good candidate for spin Hall effect or quantum spin Hall effect. Therefore, many scientists or physicists are very much interested to understand the germanium. The germanium lattice offers the possibility to open a band gap via instant and external applied electric field. So by applying external electric field, we can change the band gap, absorption of the foreign atoms, or coupling with the substrate. So that is almost quite similar whatever we observe in case of graphene. So I would like to discuss this paper. This is again seems to be the first article in buccal germanium formation on platinum 111. So here again the same structure was grown on platinum. So the substrate was platinum, and which after doing some kind of cleaning, they observed the hexagonal symmetry. So that is basically a kind of template to grow the germanium. If we are having already hexagonal symmetry at the bottom, so that is a platinum, so easily we can grow the germanium. And it another thing is that also platinum do not have very high interaction between germanium, so easily we can basically get the monolayer or absorb 2D honeycomb sheet. Otherwise, if having too much affinity, then it's very difficult to control the single layer growth. We are going to have a very multiple layer. So that affinity is not that much great. So we are just going to have very few atoms, or only just mono or bilayer or tri-layers. So germanium was first deposited onto a platinum substrate, and then after annealed, a distinct well-ordered superstructure was obtained. And the structure of germanium layered form on the platinum 1,1 substrate was then categorized or characterized by LEED. So here you can see one image of that characterization. So if you see this two color is there, the color is blue and then color is black. So basically black colored display the orientation of platinum atoms, and then this 23-degree difference, this shows basically this blue atom shows the germanium atoms, and the difference between these two is 23 degrees Celsius, 23 degree. Here again you can see the figure B. This is basically the placement of the germanium atoms, and using this even we can construct the unit cell as they have proposed here in the figure. And the line profile again shows the periodicity of the germanium structure, like up and down. If you see here, this distance between one atom to two atom, and this is basically the distance between the platinum atoms, which is at the bottom. And this was the diagram, which basically clearly give the indication how this is deposited. So you see the blue atoms are basically the platinum atoms, which are also in the hexagonal pattern, and in between we are having, see the up down structure, and the 6 atoms as a germanium atoms. And you see the even germanium atoms are also having a little bit up and down structure. So this yellow one, this light yellow and dark yellow, the light yellow is basically having slightly upper side, so they are creating kind of buccal structure. So the figure B is basically a simulated STM image which shows the identical result as we have observed in case of experimental data. This is the another paper where they have grown few layer epitaxial germanene, a novel two-dimensional derived material. And in this structure, again it was grown very high vacuum conditions. Here they have just used the gold in place of platinum, and the synthesis was done at 250 degrees Celsius. And in this study shows the height of gold atom was around 2.4 angstrom, while the height of germanium step is almost 3.25 angstrom. The atom thin sheet was achieved, which lie directly on the metal surface are likely to lose because the interfacial coupling is not so great, and the massless Dirac fermions character and other unique associated physical property of freestanding germanium was investigated. And this here you can see the figure first A. So you can see the step height. So basically 1 layer, 2 layer, and 3 layer. So it shows step and step flat terrace with the height of almost 3.2 angstrom. High resolution STM topography, large prostration arranged in a distorted hexagonal arrangement. So see here, this high resolution, again you can see the atoms are basically aligned in the hexagonal pattern. Then further structural analysis was done and which confirmed the formation of germanene. So if you are further interested, I would suggest you go through these literatures, ACS Nano, New Journal of Physics, ACS Nano, Journal of Physics Chemistry C, and one review paper. So that's, I would say, for silicene and germanene. So today I would stop here, and in the next discussion we will come with another material. Thank you very much.